Alright, this is video lesson 8 of our semester-long course in basic circuit analysis. And we're kind of turning the corner now. I think this starts a new chapter in our textbook. So in this video we're going to actually cover three related topics: this linearity, superposition, and source transformation. We're going to cover them in that order, and we're going to start by taking more of an abstract approach to circuit analysis. So first of all, you'll see I have these two circuits here that look very similar, but differ just by this voltage source here. But before we get to those circuits, I want to kind of elaborate on this more abstract approach. In general, a circuit can be viewed as a black box. Any circuit, really. And that black box usually has two output terminals, so you can connect a load resistor. Okay, and it's got some input terminals here. And I'm going to leave off the symbol here because the input can be either a current source or a voltage source. So we'll just say that this is the input over here, and the output over here. And of course, the input doesn't have to be to the left, or the output doesn't have to be to the right. But for just the sake of drawing it, this is what I've got. So this is typically what a circuit kind of can be modeled as. For example, an MP3 player, the input would be from the tracks that you've downloaded and stored on your iPod, or on your MP3 player. So they're stored into memory, and then when you push play, those audio tracks feed into some system here, some circuit in the black box, and then its output terminals would be the headphone jack. And so what would that make RL here? Well, that would make it in your headphones, and headphones actually can be very well approximated by a resistor, 20 ohms, 10 ohms, so forth. Okay, or for another example would be the input could be the wall outlet. So this would be 120 volts in the United States at 60 hertz. And then you have some sort of circuitry here. Maybe this is the circuitry of your house. And I guess if this is the wall outlet, then this wouldn't be the circuitry of your house. This could be the power line, so the power line that gets delivered to your house, and then you have the house circuitry here, and then the output would be the hopefully 120 volts at 60 hertz, and so you plug in maybe a toaster or some sort of appliance, and that's the output. Okay, so in general, circuits typically have an input and an output, at least one input and at least one output. So for right now, we're just saying exactly one input and exactly one output. So special to this class is that I want to cover what a linear circuit is now. So now we're going to make the assumption that in this box is a linear circuit. Okay, and the question then, of course, is what is a linear circuit? So at the input, as we've already said, at the input we could have voltage or current. Okay, and so I don't want to make a V or an I. I don't want to assume that there's one or the other. So I'm just going to call the input X right now, and that could be a function of time in the case of AC circuits, which we have not covered yet. There's a sinusoid there, and so that is a function of time. And similarly, at the output, we could again have a voltage or a current at the output. For example, in this picture here, we might want to know what the voltage across that load resistor is, or we might want to know the current through that load resistor. We probably want to know the power eventually. But I don't want to make any assumptions on whether or not we're dealing with voltage or current, so I'm not going to put V or I. Instead, I'll call that output Y, and Y, too, can be a function of time. So a linear circuit, then, a linear circuit is a circuit such that the output and the input are related by Y equals some constant. We'll call that constant K times X. It's a very simple equation, but if this holds, then what's in the box is a linear circuit. Okay, that's the key. K can be any number, positive, negative. If it's 0, it's kind of trivial. It won't be 0 because that means the output's 0. But it can be positive or negative. It can be an integer. It can be decimal, whatever. But if this holds, then you have a linear circuit. Okay. Well, let's come up here. Let's look at this circuit on the left, and let's try to figure out, is this a linear circuit or not? So let's say the input here is the current source X, okay, and the output here is the voltage across this resistor. All right, so in this, as if I want to draw it in this picture, in terms of this picture, then here's what's in the box, right? Okay, well, I want to determine if this is a linear circuit. So can I write Y, the voltage across the 8 ohm resistor, as some number times X, that current? So let's start to analyze this circuit. I'm going to use mesh analysis here. So, you can't forget about these things that we spent so long learning. I've got 2 meshes, I1, but I1 is 30 amps. So I've got 30 amps circling around there, and here's we'll call that I2. Okay, so I just need one equation. So if I go, if I do KVL around mesh 2, start here and work my way around, I've got let's see, KVL around mesh 2. Okay, so I'll go this way. I've got the 12 ohm resistor, so that's 12 ohms. The voltage drop is 12 ohms times I2, plus I've got the 8 ohms times I2, and then I have to come back up, so that's plus, I've got the 4 ohms times I2, and I've got the 30 amps against me, so minus 30 amps there. And I'm back to where I started, so that's equal to 0. So I've got this one equation, one unknown. Hopefully you're with me here. If not, go back to mesh analysis. So now I can combine the like terms. I've got 4, 8, so that makes 12, and another 12, so that makes 24 ohms times I2. And then the constant term here, I have 4 ohms times minus 30 amps, so that makes negative 120 volts. 120 volts, so I'll add that to the other side. Makes 120 volts. And so that means I2 is 120 volts divided by 24 ohms. So does that go in evenly? There's definitely a 10 there, so there, or excuse me, a 12 there, so that's 12, that's 10 volts over 2. Oh, it does go in nicely. That's 5 amps. 5 amps. Okay, so I've got 5 amps swirling around there. That's that hypothetical current going in there. If I want to know the voltage, then, okay, I've got V0 equals the 8 ohms times the 5 amps Okay, so that is 40 volts. All right, but remember, the question was, does this voltage, or can this voltage, be written like this? Okay, where X is this 30 amp source. So where did we use the 30 amp source in this equation? Right here. All right, so let me back up, and instead of 30 amps, let me write X. Now I'm going to be general now. Okay, that's the input, so I'm just going to call that X. All right, now remember I distributed the 4 ohms in and then added it to the other side, so this gave me 120 volts. But now, if I'm going to keep it in terms of X, okay, this is going to give me 4 ohms times X, where X is in amps. Okay, moving right along then. Now I don't have 120, I have the 4 ohms times X, right? And so I don't have 10 over 2 anymore. In fact, I'm just going to erase this. Okay, what I do have is, let's see, 4 over 24, so that's X over 6 amps. Okay, now that's the current. So you tell me whatever this is. Okay, it was 30 before. So then I2 was 5, right? 30 over 6. So you tell me whatever the input is, X, and then I'll tell you this hypothetical mesh current, X over 6. Then V0, the output, is the 8 ohms times that current I2, which is X over 6 amps. Okay, so the 8, there's a 2 there, so that makes 4 X over 3. And remember, V out is what we're calling Y. So, is this a linear circuit? Well, I've got Y, right, which is V out, equals 4/3 times X. Yes, it is. It's a linear circuit. The value of K here is 4/3. Okay, now, the reason, well, there are a lot of reasons why this is important, and you'll see that as we go through this video and the next video. Linear circuits are very important, but immediately I can demonstrate why this is important here, and that is, now you tell me, oh, X is 30, okay, 30 amps. So if the input is 30 amps, then, okay, X equals 30 amps. So that immediately implies that Y is 40 volts. Right? That's what we got. Check. And now suppose that I changed it up on you. Maybe I ask you, now, maybe the input gets changed to 45 amps. Okay? You see, things are not always going to be static, right? We live in a dynamic world where inputs are changing. You turn your iPod on, you turn your iPod off. The music is a function, itself is a function of time. Okay, so now let's say that input current goes from 30 to 45. Well, what's the output? Well, we know that the two are related like this. So now if X is 45, 45 divided by 3 is 15. 15 times 4, 60 volts. So instead of having to do the analysis again, right, where we would ramp this up to 45 amps and now we would have to do mesh analysis again and find V out, we know that how they're related, the input and output are related. So we can do the calculation quickly. All right. Now, so we've concluded this is a linear circuit. Okay, this is a linear circuit. All right, now we want to know, is this a linear circuit? You could probably guess. So I'm going to erase the KVL here. Okay, and I'll move our result over there. Okay. So now you say, well, maybe you're unsure because, well, this circuit seems very similar to this circuit, which is a linear circuit. So maybe you think it is. So we'll do the mesh analysis. This is 30 amps, and this is I2. All right, well, let's do, again, KVL around mesh 2. So if I start at the left, top left, I've got the 12 ohms, again, 12 ohms times I2 plus 8 ohms times I2. That puts me down here, and then I have a jump of 1 volt, so minus 1 volt, and then plus 4 ohms times I2 equals 0. And so I combine all these guys again, and I have 24. Oh no, excuse me. This is not 4 times I2. This is 4 times I2 minus 30 amps, but we're going to call that X, the input, equals 0. So now when I combine everything, I have 24 ohms. Okay, and then I have a constant term. I have this minus 4 ohms times X, and I also have a minus 1 volt. So now when I and times I2. So now when I get everything to the other side, I've got 24 ohms times I2 equals 1 volt plus 4 ohms times X. And so I2 is 1 volt plus 4 ohms times X over 24 ohms. Alright, that gives me this mesh current. Now if I want the output, Y, or V0, we're calling that V0, then that's from Ohm's laws, that's the current times the resistance. So that's the 8 ohms times 1 volt plus 4 ohms over X, or 4 ohms times X, over 24 ohms. So the 8 ohms and the 24 ohms makes 1/3. So we get 1/3 volt plus 4/3 ohms times X. So this part looks familiar, right? The second part here. This part looks familiar. This is what we got up here, right? But notice here, the 1 volt that we carried through, now there's this term, 1/3 volts. So take a look at that equation, right? We have Y equals 1, I'll drop the units just to make it obvious. Y equals 1/3 plus 4/3 X. Is that in this form in red? No, it's not, right? So this circuit, the second one, is not a linear circuit. Is that surprising? Well, it turns out though this circuit still is has some very nice properties to it. All right, but for right now, let's discuss why this one would be a linear circuit and this one is not. So let me erase this. Well, the circuit here on the left is made up of, and in the box, right? We're interested in the box. Is the stuff in the box? Just like the picture that I just deleted, right? Is that a linear circuit in the box? Well, the stuff in this box on the left, we just have resistors here, and we know the voltage current relationships with resistors is given by Ohm's law. So you see, this is a linear relationship, just like y equals kx. Okay, the voltage and the current are proportional to one another. All right, so any circuit that's made up of just resistors is a linear circuit. Furthermore, now this circuit did not have any dependent sources, but if we had a dependent source, okay, those are usually proportional. You know, maybe the voltage is 3 times some current, and maybe this current is 3 times some voltage. Okay, they're always in this form where you have a number times something, and that's because of transistors, which we won't get into. But so this voltage, a dependent source's voltage, is related to some voltage or current in that form as well, and the current is also related to the voltage in that same form. That is to say, they're proportional. So we conclude that any circuit comprised of only dependent sources and resistors is a linear circuit. Okay? That's big. Now over here, this box has an independent voltage source, and so you saw the trouble that brought with it. It was because of that that our input and output did not follow a linear relationship. So here, if the circuit contains an independent source, it is not linear. Okay, and you have to be careful. What we're saying is, you see this circuit over here. We're saying that the independent source comes out of the box. That's serving as our input. So when we're saying that this circuit is linear, we're saying that what's in this dashed box is linear circuit, and what's in this dashed box is nonlinear. Okay, so this dashed box does not contain any independent sources. All right. Now, a linear circuit has two nice properties. The first is, remember, the relationship here was y equals 4/3 x. The first property of linear, and I'm going to say systems. I'm going to keep this general, especially for you mechanical engineers. A linear system is not specific to circuits, okay? And these properties are not specific to circuits. You'll see in your mechanical engineering classes that any circuit made up of masses and springs and dampers, that's a linear system as well. Okay, so this is not specific to circuits. The properties of linear systems. The first is the additive property. Okay, the additive property. So, for example, for this circuit, we saw that these two things, x and y, are related by this equation. So, let's say I put in a certain input x1. That's going to give me a certain output. Okay. And if I put in a different input, x2, that's going to give me the output y2 is 4/3 times x2. And so if I put in the sum of those two things, I'm going to get out a third signal. It's going to be 4/3 x1 plus x2. And if I factor that in, or excuse me, if I distribute the 4/3 in, now this gives me y1 plus y2. So this is the math to say the following. Okay, the additive property is the output due to a sum of inputs is the sum of the individual outputs. Okay, so for example, this first circuit, I think we plugged in, what, 30 amps for x. So when x was 30, we got y to be 45. So in this mathematical formulation, x1 was 30 amps and y1 was 45 amps. Then we plugged in what? We plugged in 45 amps. Oh, 45 amps. Excuse me, the output was a voltage. The output was a voltage. Okay, so we plugged in 45 amps next, and we saw that we got 60 volts. Okay, so question, what happens if we plug in 75 amps? Notice that's x1 plus x2. What are we going to get out? Well, the output due to the sum is the sum of the individual outputs. So if we know 30 and we know 45, then when we plug in 75, we're going to get the sum of those two. We're going to get 105 volts. That's the additive property of linear systems. Okay, the second property is it's called the homogeneity. Property. Okay, the homogeneity property says exactly what we've already said, actually. That if it can be written like this, the output can be written as k times x. Then if I scale the input by some factor, so let's say let's say I plug in up here. Let's take this example. I plug in x1 and I get y1, right? And let's say I plug in a different factor now. Let's say beta times x1. I will get out beta times x2. Okay, that's the math. So in English, the homogeneity property says the output due to a scaled input is the scaled output of the unscaled input. I'll give you an example, concrete example in a second. Alright, so again, this circuit, which we've said is linear, we plugged in 30 amps and we got 45 volts out. Question, what would happen if we plugged in a new current, 60 amps, which happens to be double what we're putting in currently? So if we double the input, then what we're going to find is that the output doubles to 90 volts. Okay, that's the homogeneity property. Let's say we tripled the input, or maybe we halved the input. So maybe we took it down to 15 amps from 30 amps. So the output would also be halved. That's the homogeneity property. Now, from the two properties of a linear circuit, we can deduce a third property, and this is a big one. This is called superposition. I'm not going to prove it, but one can deduce the following. The voltage across or current through a circuit element in a linear circuit is the algebraic sum of the voltage across or currents through, depending on what you're looking at, the element due to each independent source acting alone. Okay. Remember this circuit here? And actually, I apologize. I realized earlier that I wrote this 1 volt source with this symbol. There are two ways of writing a voltage source. This way or that way. They're equivalent. So we write them in this fashion, and I had a little mind slip there and I wrote it like this. Alright, but we had looked at this circuit and we said that this circuit was nonlinear due to the 1 volt source. But now, what I want to consider is this circuit Here's the output, as always. But let's suppose, so we're moving all of the independent sources out. And we're supposing that the two sources are two inputs. So this is input number 1, and this is input number 2. And so superposition says that, in this case, we're looking for a voltage. The voltage across this 8 ohm resistor is going to be the sum of the voltage across when only the 30 amp source is activated, and we're going to turn this one off, plus the voltage across this resistor when only the 1 volt source is activated, and we're going to turn this guy off. That's superposition. So we analyzed this circuit already, and we said that the output, we called it Y, or V0. I believe we found that it was 1/3 plus 4/3 times 30. I think that's what we found. In other words, there were these two pieces. The 30 is from this source, and the 1 is from this source. And so the answer here is going to be 40.33 volts. I believe that's what we found. But the key point here is that it's a sum. The output voltage was a sum of this piece and this piece. That's due to superposition. So now I want to get this answer again, but I want to do it using the law of superposition. We're going to turn off one of the sources, find the output, and then turn off the other source and find the output, and then add them together. Before we do that, let's discuss how we would turn off a source. Okay, well, a current source, all right, no matter how many amps it is, 30 amps, 45 amps, 1 amp, whatever, if we want to turn it off, well, what we mean is we want zero current to be flowing there. So schematically, what has zero current flowing through? An open circuit, right? So we're going to turn off a current source by replacing it with an open circuit, and no current can flow. So this is the current source becomes an open circuit. And to turn off a voltage source, here's a voltage source. Well, we want 0 volts across that if we're going to turn it off. So what has 0 volts across it? A short circuit. So a voltage source becomes a short circuit. And the idea is, what we're left with in the box, if we consider the independent sources to be inputs, then what we're left with in the box is a linear circuit. So superposition applies, right? Only to linear circuits. Superposition applies, and when we turn off a source, the circuit actually simplifies, right? Because this guy would become an open, this guy would become a short. All right, so let's do it. Let's now turn off, and I can pick either one. The order doesn't matter. Let's turn off the 30 amp source. Okay, so I'm going to have an open circuit over here because I want 0 current to be flowing. So I've got the 4 ohms, I've got the 1 volt source, (12 ohms, 8 ohms, Okay, and remember, it's the voltage across the 8 ohms that I'm looking for. And I'm not going to label this as V0 because it's a different V0 now because we've changed the circuit. So I'm going to put V0 prime. Okay, it's related to the V0 we're looking for, but it's going to be different, potentially. Alright, so you see, now that I have this open circuit over here, I have one less mesh. This mesh current is effectively 0. So I only have this guy. So I only have one mesh, so I can solve for V0 very quickly using KVL. Just go around the loop. Right? So if I start here, I've got 12 ohms. I'm going to run out of space, so I'll write it down here. 12 ohms times whatever loop current is there, plus 8 ohms times that loop current. Then I have an increase of 1 volt, so minus 1 volt, and then plus 4 ohms times whatever loop current is there, and that equals 0. Equals 0. So let me solve that for I by combining like terms. I've got 12 and 8 is 20, 24I equals 1 volt. Okay, and I is 1 over 24. Yeah, 1 over 24 amps. Okay, that's I, and we're interested in the voltage across the resistor. So if that's I, that's the current going through clockwise. So what's the voltage across the resistor? Well, from Ohm's law, the current times the resistance, 8 times 1 over 24, so that's the 1/3 volts. Okay, and here's the big picture now. Notice that was this term when we did the problem at the beginning of this video. Okay, this term is the piece due to just this source. Okay, so now I'm going to scroll down a little bit. Now let's turn off just the 1 volt source. And actually, we did this already at the beginning of the video, but we'll do it again. This is the 30 amps, 4 ohms, and now I have this short circuit there, you see. The circuit simplifies when I use superposition. And I just mentioned that we did this earlier in the video. You say, well, I don't remember that. Well, yeah, so now that this is a short circuit, this circuit matches the very first circuit that we looked at. And again, I'm looking for this voltage across the 8 ohm resistor. We're going to call that V0 double prime. All right, well, so I've got this mesh current is 30 amps, right? So let me get this mesh current, call that I2. So if I do KVL around mesh 2, I've got 12 ohms times I2 plus 8 ohms times I2 plus 4 ohms times I2 minus 30 amps equals 0. So if I combine like terms, I've got 24 again, 24I2, and then the constant term is negative 120 volts. I'll get that to the other side. That's 120 volts. So that makes I2 equal to 5 amps. So if I2 is 5 amps, what's the voltage drop? 5 times 8 is 40 volts. And again, I want to point out here that that answer is this piece right here. So this is always going to be the case that for linear circuits, what the quantity that you're looking for is always going to be a sum of all the contributions from each independent source. So here we had two independent sources. Okay, so there are two contributions to the output. So that's what we just saw. So now finally superposition says, okay, if I want V0, right, V0 equals V0 prime plus V0 double prime, and so that is 40.33 volts. Done. This is big. This is huge, a huge result for linear circuits. All right, let's look at another example with three sources. So we'll have a 12-volt source there and a 24-volt source and maybe a 3-amp source. Okay, 8 ohms up top. 4 ohms there. 3 ohms. 4 ohms. All right. So there's our circuit, and let's say we are trying to find I, that current there. All right, and we're going to use superposition. Now before we get into it, I want to point out that you can use nodal analysis and you can use mesh analysis if you would like. Okay, those two types of analyses work for any linear circuit. So you can use those. Okay, but we're learning different methods now. So we're going to try superposition. So we're going to turn off it doesn't matter at this point, but we'll turn off everything but the 12-volt source. Okay, so we'll just write keeping the 12-volt source. Okay, so the 24-volt source becomes a short circuit. And the current source becomes an open circuit. So here now is our circuit, and we'll call this I prime. So we need to find I prime. All right. The great thing now is, first of all, there's no mesh over here, right? So the 8 ohm resistor and the 4 ohm resistor are effectively in series, and they make 12 ohms. So now we need to figure out how much current from that 12 ohms goes through the 4 ohm, or excuse me. Check. Okay, so now to find I prime, let's use KCL right at this node. We'll call that node X. Okay, so I have the current leaving to the left. That would be Vx minus 12 over 4. The current leaving down, which is what I want, that's Vx over 3. And the current leaving to the right, that is Vx minus 12 over, these two resistors are in series now because there's no path here. So that's over 12 ohms equals 0. Okay, I'll multiply everything by 12 ohms. So that is 3Vx minus 36 volts plus 4Vx plus Vx minus 12 volts equals 0. Combine like terms, so I've got 8Vx minus 48, so get that to the other side, that's plus 48. Okay, so Vx is equal to 6 volts. So we've got 6 volts sitting right here relative to this node here. So that makes I0, or excuse me, that makes I prime 6 volts over 3 ohms, 2 amps. Alright, so that's the contribution of this current due to just the 12 volt source. So now let's keep going and let's just keep the 24 volt source. Okay, so I've got this guy, 24 volts, in series with the 8 ohms, and the 12 volts becomes a short. Three ohms, 4 ohms, and the current source becomes an open again. And here's the current that I'm looking for. Let's call that I double prime. Okay, again, if I want to call this ground, then I can do this in a very similar manner to what I just did over here. Let's do KCL at X. Okay, so I've got Vx minus 24 now over 4. That's the current that leaves this way. The current that leaves down is Vx minus 24 volts over 3. And the current that leaves to the right is Vx minus 0 over, and then the 4 ohms and the 8 ohms are in series. So this is 12 ohms equals 0. Multiply everything by 12 ohms. It gives me 3Vx minus 72 volts plus 4Vx minus 96 volts plus Vx equals 0. Combine like terms, we got 3, 4, so this makes 8Vx, and I've got minus 72 and minus 96, and if I get that over to the other side, I've got 168 volts. 168. Okay, and so Vx is equal to 21 volts. So if I want I double prime, that would be the voltage here, which is 21 volts, minus the voltage here, which is 24 volts, over 3 ohms. So this makes minus 1 amp. And don't be concerned about the minus sign, that just means the current is actually going up. Alright, finally, let's keep the 3 amp source. So both voltage sources become short circuits. Okay, so there is our circuit now, and here's the current we're looking for. Call that I triple prime. Okay, we need to get that guy. The best way to get this, let me scroll down a little bit. The best way to get this is to use, let's see, we could use nodal analysis or we could use mesh analysis. Let's use mesh analysis. So here's a mesh current, call this capital I1, here's capital I2, capital I3. Okay, we know right away that I1 is 3 amps from the current source. So KVL around mesh 2, okay, that's 4 ohms times I2 minus I3, then plus 3 ohms times I2 plus 3 amps equals 0. Okay, I'll combine like terms. 4 and 3 is 7 ohms, I2, and a minus 4 ohms, I3, and the constant term is minus 9 volts. Okay, KVL around mesh 3. So this gives me 8 ohms times I3 plus 4 ohms times I3 plus 3 amps plus 4 ohms times I3 minus I2 equals 0. Combine like terms, put it in the same form as this guy. So how many I2s do I have? Just the minus 4 ohms. I2. I3, I have 4, and 4 is 8, and another 8 is 16. 16 ohms I3, and then the constant term is minus 12 volts. Okay, so I need to solve this system. Notice if I multiply this equation by 4 and add it to this equation, I3 drops out. So let me do that. So I've got 4 times 7 is 28, minus 4, so I've got 24 ohms I2 equals, okay, negative 36 minus 12 minus 48 volts. So we see that I2 is minus 2 amps. Alright, that makes then I triple prime, which is what we're looking for. That's I2 plus I1. That's minus 2 amps plus 3 amps equals 1 amp. So, superposition says that the current in the original figure, so here's the original figure on the top left of the board, that current is the sum of 3 pieces, right? So that would be I prime, which is 2 amps, plus I double prime, which is minus 1 amp, plus I triple prime, which is 1 amp, equals 2 amps. So this, in the original circuit, this is 2 amps. Alright, and finally, the last thing I want to cover here is the process of source transformation. Which is simple to understand. We're going to take a circuit with a voltage source in series with a resistor. Okay, so if you like to think, let's call this V. Yeah, let's call this V and R TH. Call this V and RTH. And so if you want to think of this as a building block, we're going to exchange this building block for a different one, a current source, I. I'm going to leave off the arrow for right now. For I in series, or in parallel with a resistor, call it R N. Okay, so the idea is that we've got this building block in a circuit, and I'm going to exchange this building block for this one. Can I do that? Yeah, so I'm transforming a source from a voltage source to a current source. Can I do that? And you know, if so, then what is the relationship between the resistors and the voltage and the current, such that the transformation is equivalent? Now, we've seen equivalent transformations before with combining series resistors and parallel resistors and delta Y conversion. And the idea of equivalence is as follows. If we took, let's say, this first picture, okay, and we connected it to something, right? It's connected to something. So inside the black box, we don't know, but we know that there's a voltage there. Call it V in. And we know that there's a current here. Call it I in. Remember, the notion of equivalence is that if I do this correctly, if I've done the transformation correctly, then when I connect that same circuit, same box, right, I get the same voltage and the same current. Okay, if the voltage V in is the same as the voltage V in here, and if the current I in is the same as the current I in here, when the two black boxes are the same, then this is an equivalent transformation. Okay, and so I want to figure out how to do that transformation. Given this box, this picture, how do I transform it to this picture? Okay, and you'll have homework problems where you'll see why you want to do that. Okay, that I'm not going to cover. Alright, well, let's start with a simple black box. Let's say the black box is simply an open circuit. There's nothing in there. If this is an open circuit, then the voltage Vin is equal to V. That must be true because In would be 0, and there's no voltage drop across that resistor. If there's no drop, then the voltage here, which is V, must be the voltage here, which is Vin, so this must be true. Okay, now, remember we said the notion of equivalence, if I connect the same thing. So now I'm going to connect an open circuit over here. All of the current, then, has to go through Rn. Okay? Has to go through Rn. So, that means the Vin here, the voltage that develops across this resistor, if the current is going up, right, then that current comes back down through the resistor, and Vin is equal to I times Rn. Alright, so now we have a small piece of the puzzle how to perform this transformation. We know that the current, right, if we compare Vin here with Vin here and solve for I, we know that the current source must be the voltage source divided by Rn. Okay, and we know that the direction of the current is in such a way that it has to be pointing from negative to positive of the original voltage source, because that current again comes down this way and makes the voltage drop from top to bottom, right? So we're going to add that to our picture here. Alright, now let's consider not connecting an open circuit, but a short circuit. Now we're going to connect a short circuit. We can connect anything, right? Because if it's an equivalent transformation, it does not depend on what we connect, that the voltages and the currents must be the same. Okay, now here, Vin is equal to 0. And Vn is equal to 0 here. But how much current do I have? In this picture, I have In is equal to V over R Thevenin. Excuse me, RTH. And here, I have I. The reason I have I is because this resistor here has been shorted. It's been shorted. So all of the current, right, there's no voltage across this resistor. So all of the current must go through the short. No voltage across the resistor means no current through the resistor. All of the current goes through the short. So now comparing this guy with this guy, we see that I is equal to V over RTH. Well, now compare these two equations, right, that we just wrote down. If those are to be true, then the resistors in each case are equal. So let's just call that R. They're equal. So we'll drop the subscripts. And so we've completed the transformation. So let's be concrete about this now. Suppose you were given maybe 9-volt battery, and a 1 ohm resistor, and maybe this is connected to something like this. Maybe we have 5 ohms here, 11 ohms here. Okay? I can transform this to the following picture. Like this. And you see, the resistors are the same. That's what we just showed here. So I just copy and paste. I copied this 1 ohm resistor, I put it here. And the current source, what we showed is the arrow of the current source goes from negative to positive, right? And the value of the current source, well, this must be true, either equation 1 or equation 2. 9 volts is V divided by the resistor 1, so this would be 9 amps. Those are equivalent circuits in the sense that everything in this box, meaning the voltages and the currents, powers, have not changed. Anything in here, any quantity in here, external to the transformation, right? The transformation happened over here. External to the transformation, everything stays the same. That's an equivalent transformation. And it works the other way as well. If we were given this picture, we could come back, so the arrow goes to the left as well. We could go back to this picture if we wanted to. And just foreshadowing for your homework, why would you want to transform? Well, imagine you have the picture on the left. Then you transform to the picture on the right. Now the 1 ohm and the 5 ohm resistors are in parallel, so you can combine them. Right? You could not have done that here in the picture on the left.